If you want to avoid the torture to a certain extent, you have to pay attention and you have to master the different rate conversion factors that is applicable for the two different catalyst types that I just discussed. So for that purpose, this next slide will consider some geometric calculations and some applications that is very important for you to master before you continue with the rest of the work. First, note that in CRO we are going to only consider spherical catalyst types. Perfect spheres, and even more so, we are going to assume that we have a single particle size distribution, so we don't have a range of particle diameters that's present in our catalyst heap or our catalyst mass that we are going to feed to our reactor. It is important to note that you can actually have several different other shapes of catalysts. You can extrudates that looks like little spheres. They can even have a little hole inside, shaped specifically to allow for better mass transfer, this shape. But as I mentioned, for our course, we are only going to focus on perfect spheres when we consider the geometry of our catalyst particles. For that purpose, you need to remind yourself of the external surface area of a sphere. What's the amount of external surface that's available? And you need to be able to calculate the volume of a sphere. And we are going to need that when we calculate the area per volume of a perfectly spherical particle. And we will, of course, note that that simply then depends on the size of our sphere, the diameter of our sphere. The smaller our size, the bigger the area available per volume of catalyst. And we talk about area here, just referring to the external surface area that is relevant for the diffusion, external diffusion process. Not to be confused with this SI. So we are going to use SI for our porous catalyst type to denote all that internal catalyst surface due to the catalyst morphology that is available. Other variables that is important is that I have a catalyst density. So the catalyst density refers to the material of which the catalyst is made, including the porosity of the structure. So that is a measured quantity, kilogram per cubic meter catalyst. And then how much catalyst do I have per reactor volume? That is one of the important rate conversion factors. And of course, for a packed bed reactor, that is the density of my packed bed that I can relate to my catalyst density using the bed porosity. Once again, this bed porosity not to be confused with the catalyst porosity that we are also going to use in later calculations. And then, of course, for a CSTR, what is the mass of catalyst that we have per volume of my reactor? The symbol we use there, even though it's got the same unit systems, that is the catalyst concentration that is present in my CSTR reactor. First parameter we are interested in defining is the one for which we use the symbol AM. So A, small a, just make a note for yourself, always refers to the external surface area, and the M here says we must calculate what is the amount of external catalyst surface area that's available per kilogram of catalyst that we have in our reactor, either in a packed bed reactor or in a CSTR. So we start this calculation by first defining the area per volume of our catalyst. That will give me meters squared per cubic meter catalyst. And then I want this to have units of meters squared external surface area per kilogram catalyst. So I have to convert that using something that's got the appropriate units. In here, the 1 over the density will have cubic meter catalyst per kilogram catalyst. So in other words, for my sphere, I can calculate that related to the catalyst density. For a packed bed reactor, I can replace this catalyst density by the bed properties by realizing that the catalyst density is simply equal to the bed density divided by 1 minus the porosity in my reactor. So we can have looks like an extra equation that's just applicable to our PBR, that if I have the packed bed density and the porosity, I can relate that to my available external surface area per kilogram catalyst in my reactor. This equation applies for a sphere for either a packed bed reactor or a CSTR. The next conversion factor that we want to define is A subscript C, AC, if we're going to talk about it. And that is the symbol that wants to tell us what is the amount of external catalyst area in meters squared that you have available per cubic meter, but now not per cubic meter catalyst, but per cubic meter reactor. So if I have a 5 cubic meter CSTR and I know the value of AC, I will be able to calculate the total external surface area of my catalyst that is present in that reactor. For me, it is easier to start this for a packed bed reactor in a CSTR, two different equations for this parameter. Start with the packed bed. What is AM? And for AM, I have the equation. It gives the meter squared or the external surface area per kilogram catalyst. And all I now need is a factor that tells me what is the amount of catalyst that I have present in my reactor. And for a packed bed reactor, of course, that is the packed bed density. But for a CSTR reactor, that conversion factor is the catalyst concentration in kilogram catalyst per cubic meter reactor. So where does this fit in? So what we must remember is that our true rate constant, and I use this intrinsic rate constant symbol to denote that we are talking about a rate constant that is free of any diffusion transport limitations, actually depends on the amount of active sites that I have on my catalyst surface. And if we have our just to torture solid catalyst, those external sites is only available on the external catalyst surface. So this rate that we can then say, and we're going to denote the triple dash to talk about the rate per active site, says how fast can my reaction take place based on the amount of active sites that is available on my catalyst surface. Of course, the concentration that is relevant as it reacts is the one that has already reached that active surface. So it's not necessarily the bulk phase concentration. It is the one that is present after the diffusion process took place. So now we consider a parameter that says what is the loading density. Let's use L sites for that parameter. How many active sites do I have per catalytically active area? So this is a catalyst specific parameter. So if I want to convert my rate to give me an rate, how many moles per second of A gets converted per area of my catalyst, I can take this rate that gives moles per second per active site and multiply it by my loading density. How many active sites do I have per external surface area in the case of a solid non-porous catalyst? That will give me the rate based on the area of the catalyst that is available in my reactor. We use this double dash to just remind us that we are now referring to rate based on the catalyst area that is covered by a certain amount of active sites. So in other words, how can I change my catalyst? If I change the catalyst, if I increase or decrease the amount of catalyst active sites that I have, the loading density, I will therefore change my rate area based rate constant. But normally, we would be interested in expressing our rates per kilogram catalyst that we add to our reacting system, so that our independent variable is actually the mass of catalyst. So in other words, if I have the solid catalyst, so the non-porous catalyst, the conversion factor I am going to use here is AM. Just a reminder, AM gives me the external surface area per kilogram catalyst. It is a geometric calculation and it depends on the shape, and for our spherical shapes we have 6 over the particle diameter, and we use the catalyst density for that conversion factor. For our mass-based rate, the rate at which A gets converted per second per independent variable catalyst mass, we are used to this single dash symbol that we use to denote that. We also use that for our rate constant. For our solid catalyst, I can't stress this even more, that this is the torture catalyst that is not porous. So the area that we must use here is our external catalyst area and not the total SI of net pore networks that's available that we should use when we have a porous catalyst particle. And lastly, if we want to base our rate, use our independent variable as the reactor volume, we need a conversion factor, and please note there the absence of any special markings, because that is the rate at which I convert A per cubic meter of my reactor. So I now have my rate per kilogram catalyst that I need to convert by multiplying it by the appropriate factor that gives me the amount of catalyst that I have in my reactor volume. And once again here I'm going to use the catalyst concentration in a CSTR and the packed bed density in a packed bed reactor. So our volumetric rate constant depends on how much catalyst I can fit in my reactor. For a CSTR, that is a variable. I can add more or less catalyst in my reactor and change the concentration. Whereas for a packed bed reactor, that is a function of what is my catalyst concentration and what is the porosity in my catalyst bed. What we should denote is that if I have spherical particles and I have a big enough wall to particle ratio so that the wall does not affect my particle structure, even if I make my particles bigger or smaller, the bed porosity goes to the limit of pretty much 0.4. So that may not be as variable as you think for a packed bed reactor. We are going to assume that this protocol holds and that our packed bed density is constant regardless of our particle diameter, and in fact it goes to the asymptote for spherical catalyst particles where that bed porosity is 0.4. If I run the calculations in reverse, I can therefore show that my volumetric rate constant for a CSTR is equal to this true intrinsic rate constant, Ki triple dash, which says how much gets converted per active group that I have present. It then still depends on what is the loading, the density, how much of this stuff do I have available per meter squared of my catalytically active area, multiplied by how much of that catalytically active area do I have per kilogram catalyst. This thing is to be replaced by SI for my porous catalyst structures. But for the solid catalyst we are busy considering, and that we are going to consider for theme 6, this will depend on AM. And of course, AM on its own is inversely proportional to my catalyst particle diameter. So that implies that Ki is going to change if I change the density of the sites, the site loading on the active area. It is only also going to change if I change my catalyst particle diameter. And ultimately in the CSTR, it is also going to increase or decrease depending on the amount of catalyst that I have present in my reactor. For my mass-based rate constant, that will give me the rate per kilogram catalyst in my reactor. Once again, I can follow my train and I can see that it is directly proportional to this true rate constant that gives me the turnover rate per catalytically active sites. How many sites do I have per catalytically active area? For my solid catalyst, it is going to change with AM and therefore also inversely proportional to my particle diameter. Once again, note, for the porous catalyst, we are going to replace AM with SI because most of our catalytically active surface area will be inside this porous catalyst matrix.